Chapter 7 was called The Mole, and we were introduced to the mole, which is the very important quantitative unit that we learned about in chemistry this year. The mole is nothing more than a unit that helps to describe a really large number of things. I kept emphasizing that the mole works exactly like a dozen works. A dozen represents a grouping of 12 things. A mole just represents a grouping of a really large number of things, and that number is 6.02 times 10 to the 23rd things. It's called Avogadro's number, after the scientist who helped sort of discover this idea of quantifying matter and quantifying particles. So things that are important to understand when we talk about a mole of a substance, we're referring to 6.02 times 10 to the 23rd, or 602 sextillion particles of that substance. Whatever that particle is depends on what the representative particle is for that substance. If it's copper, it's an atom. If it's water, it's a molecule. If it's sodium chloride, it's a unit. But it depends on what the substance is and how the substance is bonded together. The image here is showing us what a mole of carbon would look like versus a mole of copper. They'd have the same number of atoms, just like if I said I had a dozen bagels versus a dozen eggs. I would have the same number, but the mass, total mass, would be different because the mass of each individual item is different. And the same thing here. The mass of each individual carbon atom is different than the mass of a copper atom, so the total mass is going to be different. We looked at the molar mass of substances. The molar mass is a value that tells me for 1 mole of a substance, what is the mass of that mole in grams. So if I had 602 sextillion water molecules, what would the mass in grams be? Or 602 sextillion ammonium chromate units, what would the mass be? Or 602 sextillion barium nitrate units, what would the mass in grams be? And what we can do is use the periodic table. We developed the idea in this chapter that the masses in the periodic table are not just average atomic masses. We can use them as average atomic masses where the units are AMU, but Avogadro's number was sort of set up to be that specific number so that we can use the masses on the periodic table for a second purpose, which is, instead of saying, you know, the average mass of carbon is 12 AMU, right, the average mass of a carbon atom, the average mass of a mole of carbon, if I had 602 sextillion carbon atoms, the mass would be 12 grams. So the number was fixed in that way so we can use the masses on the table for a second purpose. So to find the molar mass, we consult the periodic table, just add up the masses of all the atoms together, and we get the molar mass, which has units of grams per mole. We should be able to answer simple questions like these that are here. Which has more mass, 1 mole of chlorine or 1 mole of arsenic? We can consult the periodic table. 1 mole of chlorine has a mass of about 71 grams, where a mole of arsenic has a mass of about 75. 1 mole of cobalt versus 2 moles of aluminum. 1 mole of cobalt has a mass of about 59 grams, where 2 moles of aluminum would have a mass of about 54 grams, so 1 mole of cobalt wins there. And then 4 moles of water, or 3 moles of CO2. A mole of water is about 18 grams, so if we have 4 moles, that's about 72. Where 3 moles of carbon dioxide, which has a molar mass of about 44, that would be 132, so 3 moles of carbon dioxide wins there. Now, in terms of, if I given gram amounts, which has more moles, I'm looking which is closer to being a molar mass, or the mass value that has more moles in it, right? So a mole of chlorine or a mole of aluminum, well, chlorine being diatomic has a mass of 71, right? So there's about 4 moles in 300 grams of chlorine. Where in 300 grams of aluminum, if we check the periodic table, aluminum has a molar mass of about 27. So there's way more moles in 300 grams of aluminum. The one that has the lower molar mass is going to have more moles in equal gram samples. 100 grams of aluminum or 200 grams of mercury. We check mercury on the periodic table. Mercury has a molar mass of about 200, so that's just 1 mole, right? So 100 grams of aluminum wins. And then 300 grams of iron, which has a molar mass of about 56 grams per mole, and 200 grams of chromium, which has a mass of about 52, if I'm looking at this correctly. Yeah, about 52 grams. So if we think, we could do a quick calculation here if you can't do it in your head, but 200 grams of chromium has about 4-ish moles in it, where I have 300 grams of iron here. The molar mass of iron is 56, so it's about 5 moles. So more moles than 300 grams of iron. So we should be able to do those just by referencing the periodic table. And then these are some of the questions that were more familiar in terms of mole conversion questions. So how many molecules do 5 moles of water contain? We start our conversion with 5 moles of water. We have different conversion factors we can use. The one that's going to help me here is Avogadro's number that says in 1 mole of water there's 6.02 times 10 to the 23rd molecules, right? Moles of water cancel. I'm left with molecules. That's the setup there. I'm not actually going to calculate them here. I'm just going to set them up. The setup is more important. The rest you should be able to just plug into your calculator. How many grams does 2.5 moles of copper weigh? 2.5 moles of copper. Avogadro's number is not going to help me here, but what is going to help me is the molar mass. The molar mass tells me 1 mole of copper is about 63.5 grams. 70 grams of fluorine, we have to remember, is diatomic. We want how many moles of atoms, not how many individual atoms, but how many moles of atoms. So fluorine has a molar mass of about 19, so double that because it's diatomic. Its molar mass will be 38. And then how many molecules are present in, can't see what that says, but I think it's 88 grams of carbon dioxide. So this one we have to use the molar mass first and convert from grams of carbon dioxide to moles of carbon dioxide, and then use Avogadro's number as a second conversion factor to convert from moles to molecules. And that's how we would do this. This little mole map here is showing us that what relates like the mass of something to its number of particles to its volume if it's a gas is the mole, right? So everything is about getting to moles. That sort of ties all of these other different quantities together. After looking at mole conversions, we looked at some applications of what we could do with the mole. And one was calculating percent composition, which is if we have the molar mass, or we calculate the molar mass of a substance like sucrose has a molar mass of 342 grams per mole, we can then take the mass of carbon in sucrose divided by the molar mass and get a percent. And then the mass of oxygen in that substance divided by the molar mass and get a percent, and the mass of hydrogen. So we know what percent by mass each element exists. We can also take the percent and we can go backwards and figure out what the empirical formula is, and then with more data what the molecular formula is. And this is going to be a weird example with sucrose, but I'm going to show you anyway, just to review some of the things that we looked at. If we assume we have 100 grams of the substance, then the percents can become grams, right? 51.41% of 100 is 51.41 grams. So if that's the case, I'd have that much oxygen, that much carbon, and that much hydrogen. We're going to divide each of them by their molar masses, respectively, to get how many moles we have for each substance. And if we do that, we're going to get about 3.21 moles of oxygen, 3.51 moles of carbon, and 6.48 moles of hydrogen. And then what we want to do to find the empirical formula is divide by the lowest mole amount that we have, because an empirical formula is the lowest mole ratio. And when we do that, we're going to get 1 here. We get 1.09 here, and we get about 2 here. Now, that 1.09 is weird. It's really not enough for us to round down to 1. It's not close enough for that. So the only way to get rid of it, we're going to multiply everything by 11, which turns this into 11, this into 12, and this into 22. And we get the empirical formula C12H22O11, which happens to be sucrose's molecular formula as well. If we found the mass of this, we'd find that it matches the molar mass of 342 grams per mole. The only other thing we did at the end of this chapter was apply the same process we did above to hydrated compounds. We named hydrated compounds, wrote formulas for hydrated compounds. They were ionic compounds that contain water in their crystal structure. If we did an experiment where I had some copper 2 sulfate hydrate, 0.2116 of it, and then we heated it up to evaporate the water, and I had 0.1353 left. If we do a quick subtraction, we see that 0.0763 grams were water, right? That plus this should get us the original mass back. And if we know that, we should be able to figure out the mole ratio. For the copper sulfate itself, if we find the molar mass of that, copper plus 4 oxygens plus 1 sulfur, we should get about 160 grams. We know water has a molar mass of 18 grams per mole. And if we do this math, 0.1353 divided by 160, we get 0.000845. And 0.0763 divided by 18, we get 0.004238. And then if we divide by the lowest amount, which is going to be this one, obviously, 0.000845, we get about 5. So that tells me the missing number here was 5, so this is copper 2 sulfate pentahydrate. So we, after going through mole conversions, we looked at some different applications where we could make the mole useful for us in finding formulas, finding percent composition, and different calculations like that. So this brings us to the end of Chapter 7, which covered the mole.